Hello everyone, my name is Abhishek Sahu, and for my project exam presentation, I will be discussing a paper from ICLR 2025 titled LORA Pro Optimization Overview. This paper introduces a new enhanced method for parameter efficient fine tuning that significantly improves the stability and performance of large language model. So let's begin by defining the core problem. We'll note that the foundation model are incredibly powerful. However, training them from scratch or even fully fine-tuning them, what we call it effectively, is extremely expensive. It's quite messy amount of computation and memory. To solve this, family of methods called PEFT or parameter efficient fine-tuning was developed. The most popular of these is LoRa. LoRa is very efficient, but it has well-known weakness. Its performance is almost always inferior for full fine-tuning. This paper investigates why this performance gap exists and propose a new solution, LoRa Pro, to fix it. The solution presented is LoRa Pro. At its core, LoRa Pro is an enhanced version of LoRa that focused on stabilizing the training of the low-rank matrices. The benefits are clear. It reduces memory and compute costs just like a standard LoRa, but it significantly improved the convergence and stability of the LoRa matrices. It's designed as a plug-and-play modules, meaning it can be easily added to any transfer model, and most importantly, it maintains or even improves accuracy, helping to close the performance gap we just discussed. To understand how LoRa Pro works, we first need to take a look at the specific problem to aim to solve. The standard LoRa simply add a product of two low matrix B and A to the original weight, and the authors of this paper identify this key problem with this simple approach, rank collapse. This is a critical issue where the low rank matrices B and A lose their expensive power during the training and collapse it, representing only a few directions. Unstable optimization. The training process of LoRa can be very unstable, especially at the beginning, leading to the poor convergence. Layer inference. The updates in one LoRa layer can negatively influence, and the update is another problem. LoRa Pro tackle all these problems with the three specific improvements, which we will now walk through one by one. The algorithm begins with the step one initialization, like standard LoRa. It initialize the low rank matrices A and B from a normal distribution, but it's add a crucial new variable, a progressive coefficient, which they can call lambda, and it's initialized to zero. The lambda zero is a key. It's mean that at the very beginning of the training, the LoRa adopt has almost zero is efficient effort. This prevents the large unstable gradient spike that of, often happen in the first few steps of the standard LoRa and ensures that training process starts smoothly. This begin up the step two, the progressive update, which gives the pro to the LoRa Pro. Instead of just adding the LoRa matrix from the start, their contribution is scaled by this lambda coefficient, as you can see from the lambda formula. Lambda t is gradually increased at the training step by t, a small growth rate eta, until it reaches the maximum of 1. This acts as a warm-up, gradually fading in the LoRa adapters influence. This avoids shocking the model with large updates and leads to much better stability convergence. Next, step three addresses the rank collapse problem. LoRa Pro introduced a new loss term called orthogonal direction regularization, or lambda orthogonal. This is the formula adds a penalty if the row of the matrix A or column of the matrix B are not orthogonal to each other. By pushing A, A transpose, AT, A transpose T, and B transpose T, B, to be the closed identity matrix. It forces to the LoRa adapt to learn diverse and independent direction. This ensures the effective effective rank stays high, prevent the matrices from the collapsing and reducing inference between layers. Step 4 is adaptive scaling. This is another problem of improvement. Instead of using single fixed scaling factor for all layers in the model, LoRa Pro introduces the alpha T, a learnable scale parameter for each LoRa layer. This is alpha is optimized right alongside the model's weight. As you can see in the final weight update formula, this allows each layer of dynamically learn how much it should rely on the LoRa update. Some layers might learn to have a large alpha, while other might learn a small one, making the entire fine-tuning process more flexible. Finally, step 5, join the optimization. Combine all these pieces. The total loss function L is a sum of these parts. First, the main task loss, which is just a standard objective like fine-tuning the LLM. Second, our new orthogonal regularization term is scale by beta to ensure the LoRa matrix learn diverse directions. And the third, a small scale penalty on the alpha t parameter to keep the from growing too large. The mod is then trained to minimize the complete loss function. So does this actually work? The results are very impressive. This table shows LoRa Pro's performance compared to the best performance baseline like Dora and Ada LoRa on several major LLM benchmarks. As you can see, the LoRa Pro consistently outperformed the previous state of the art. It's achieved significant gain of 8.4% on Alpha 2 and 3.9% gain on the math reasoning benchmark GSM 8K, and a strong improvement across all other tasks. This clearly demonstrates its effectiveness. This brings us the crucial question of the efficiency. Do all these new calculations add a lot overhead? This answer is no. Compared to the standard LoRa, LoRa Pro adds only about 4 GB of GPU memory and about 10 minutes extra timing. This is a tiny cost when you remember that full fine-tuning requires massive more memory, like 40 GB or more. This reason the cost is low is that these new calculations like the orthogonalization are performed on tiny R by R matrix. For example, an 8 by 8 or 16 by 16 matrix, not a massive million parameter model weights. So we get a significant boost in the performance and stability for a cost that almost identical to standard LoRa. To conclude, this paper identified key insightability in standard LoRa, namely rank, collapse, and unstable update. It's then proposed LoRa Pro a solution that directly fixes these problems through three key innovation: a progressive update scheduled by stability, orthogonal regularization to prevent rank collapse, and adaptive scaling to let each layer learn its own importance. The result is new state-of-art method for parameter efficient fine-tuning that is stable, efficient, and highly performance, effectively closing the gap with full fine-tune. Thank you for all attention. I'm happy to answer any question.